Hello everyone, my name is Useinov, and my topic is Skyrmion resistance within the ballistic transport model. So we simulated the Skyrmion resistance using the so-called point contact model, and our system is a point contact which is attached to the magnetic stripe with a single Skyrmion. We consider only static problem where we apply the spin polarized current through the leads. Since the spin polarized current somehow react on the local magnetization of the Skyrmion, so we have the related potential energy profiles. And spin polarized current we consider as two types. First type is the spin polarization is aligned perpendicular to the transport direction. And second case, when the spin polarization is aligned along transport direction, case 2. For the case 1, the potential profile for the spin down will be as a blue solid line like this. And for the case 2, the potential energy profile for the electrons for the spin down will be like this. A few linear based sections. Actually, these potential profiles are simplified by linear approach. The point contact model applied within only ballistic approach. It means that the diameter of the Skyrmion, dsk, have to be less or comparable with the mean free path of electrons. So the current density proportional to the summation by spin from the integrals by parallel component of the kinetic energy of the electrons. Parallel means along the interface of the point contact. And the transmission coefficient includes the voltage, parameters of the barrier, and energy. So knowing the current density and the current, we can estimate the Skyrmion resistance as a difference between point contact resistance with Skyrmion and without Skyrmion. Without Skyrmion, it means that transmission coefficient equals 1. And for the Skyrmion, transmission coefficient is derived according to the analytical view of the potential energy profile. So as a result, we have the ballistic resistance ratio, which shows how large difference between current densities is. We found that Skyrmion resistance can change in the wide range between 1 kilo ohm to the 60 ohm when the diameter of the Skyrmion changes from 1 to 6. In the second case, the Skyrmion resistance is larger. We also derived the resistance and BRR as a function of the spin asymmetry delta. We found that there is some threshold for the second case because when we approach two Fermi levels for minority and majority bands, the size of the barrier decreases, as well as the Fermi wave vector for the minority band increases, giving the increased wavelengths of electrons. From these two factors, we have enhancement of the penetration through the barrier, and this resistance degrades faster than before this threshold. So finally, we take the typical size of the possible Skyrmion. So for example, for 3.6 nanometers, we have around 157 for the case 1 and 480 ohms for the case 2. And this slide shows our results. Thank you for your attention.